All right, should I start?
Mm-hmm.
All right, hi everyone. It's my pleasure to present to you today Aditya Hegde, who's a second-year PhD student at Johns Hopkins University, who's working with Abhishek Jain and Matthew Green, and he's going to talk to us about scalable multi-party garbling. Okay, take it away, Aditya.
Thank you for the intro, Rawan. So I'll be talking about scalable multi-party garbling, which is joint work with Gabriel Beck, Arushi Goyal, Abhishek Jain, Zhengzhong Jing, and Gabriel Kapchak. Feel free to interrupt me at any point if you have questions or yeah. So this talk is all about MPC. So before we get started with anything else, let's start by first understanding what MPC is. So multi-party computation is a cryptographic primitive that allows a set of mutually distrusting parties to compute a function over their joint inputs. And the guarantee that MPC provides is that if an adversary corrupts a subset of parties, the adversary doesn't learn anything other than the function's output and the inputs of the corrupt parties. So in recent years, there have been significant improvements in the efficiency of MPC protocols, which has led them to being led to MPC being considered for some very interesting applications like machine learning over large data sets or providing data as a service and using MPC to secure digital assets and in key management. And some of these applications some of these applications require actually running MPC over the internet. And in these cases, actually the network latency limits the protocol runtime. And a large class of MPC protocols have round complexity, or rather the number of times parties should interact, proportional to the size of the circuit. Specifically, the number of rounds is proportional to the depth of the circuit. And this can, in high latency networks, this can be a significant bottleneck in the protocol runtime. So constant round MPC, on the other hand, are a class of MPC protocols which basically have require the parties to interact constant number of times. This means that they perform much better than protocols which have round complexity linear, for example, in the depth of the circuit, because especially over like high latency networks. So this enables evaluating very large depth circuits over the internet. So there are two main approaches to getting constant round protocols. One is using fully homomorphic encryption, and the other is using multi-party garbling. So in this talk, we'll focus on multi-party garbling because with the applications we're interested in, the size of the computation and so on is large enough that FHE doesn't seem completely practical. So the best known constant round MPC protocols, or rather multi-party garbling protocols, have a total communication cost of n squared times c, where n squared is the number of parties and c is the size of the circuit. So here I'm only actually highlighting the terms that really depend on the circuit size, and I'm ignoring certain additional additive terms. Moreover, this is also, for example, there's a dependency on the security parameter, which I'm ignoring. So I'm really only focusing on the interplay between the number of parties and the circuit size. And since these protocols scale quadratically with the number of parties, it's hard to use these protocols with very large number of parties, because as the circuit, the computation gets larger and the number of parties gets larger, the costs just blow up. On the other hand, in the honest majority setting, there are a class of protocols which again have round complexity linear in the depth of the circuit that achieve like a total communication complexity of order C. That is, their communication complexity is independent of the number of parties. With respect, again, here when I say that, I'm only really focusing on terms that are dependent on the circuit size. So there are no terms that have like n times C or anything of that sort. But yeah, I'm ignoring certain additive terms. And the main question we ask in this work is essentially, can we somehow get the best of both worlds? And what we mean by that is, we know constant round MPC protocols are preferred in high latency networks and doing MPC over the internet. And can we somehow bring these constant round MPC protocols in the regime of honest majority order C communication MPC? So why should we even care about order C communication MPC? So one of the cool things about MPC protocols that have order C communication, that is the total communication of the protocol is independent of the number of parties, is that there is some sort of distribution of work. That is, the per party communication actually decreases as you add more number of parties to the MPC protocol. This means that the MPC protocol can scale to hundreds and thousands of parties. And since it can scale to such a large number of parties, the honest majority assumption is more plausible in the setting, because it's harder for the adversary to corrupt a majority of the parties because of the sheer number of parties involved in the computation. So our work proposes a scalable multi-party garbling protocol that has order C communication complexity. It achieves malicious security with abort. It's in the honest majority setting, and it's based on the LPN assumption over large fields. And our estimates show that the protocol is quite practical and concretely efficient. And for example, it has a per party communication cost of around 700 MB when you garble the AES 128 circuit with around 250 parties. So the agenda for today's talk will be, I'll be first going over the structure of the garbled circuit. So we essentially need to slightly modify the standard garbled circuit structure so that it's more suitable for multi-party garbling, specifically for order C garbling. Then I'll be actually going over the multi-party garbling protocol and trying to better understand how the garbled circuit is actually computed through MPC. And finally, we'll be going over some efficiency analysis of the construction. So let's start with the structure of the garbled circuit and how the garbled circuit should be computed when so that it can be used for multi-party garbling. So as a refresher, let's quickly go over two-party garbling. So in the two-party garbling, we have a garbler that computes or encrypts the truth table. For example, it encrypts the circuit, and it sends this encryption to the evaluator, who then evaluates it to compute the output. So what does the garbler's work look like? So let's say we have an AND gate, and the truth table gate is given here. So the garbler first samples a pair of wire labels for each wire in the circuit. And for example, one of the labels corresponds to the 0 input and the other corresponds to the 1 input. It then basically substitutes the wire labels in place of the truth table. And the core idea is to encrypt the wire label on the output wire with the wire labels on the input. So for example, since 0 and 0 is 0, we encrypt the wire label for the 0. We encrypt the 0 label for the output wire using the 0 labels for the input wire. And we do this for all rows of the truth table. And the actual garbled circuit is actually a random shuffling of these encryptions. So here I've just defined how to garble a table, but we can essentially do this for all gates. And the concatenation of all garbled tables is the garbled circuit. The garbler then computes this garbled circuit and sends it to the evaluator. And now let's go over how the evaluator actually evaluates it. So the evaluator also receives, for example, let's say the X input was 0 and the Y input was 1. The evaluator also receives the labels, corresponding labels on the input wires, right? And using this, what we can see is basically exactly one row of the truth table, of the encrypted truth table, can be decrypted with any two given labels on the input wires. And the ciphertext that the evaluator can essentially decrypt corresponds to the output of evaluating the gate on the given inputs. So once the evaluator obtains the label for the output wire, it can then just continue to do the same thing for subsequent gates. So privacy here, or security here, follows from the fact that the evaluator learns exactly one wire label for each wire. But an important question is, how does the evaluator know which ciphertext to actually decrypt? So a standard technique here is the point and permute technique, where we basically color the wire labels. So for example, here each wire label is colored arbitrarily in like orange or green. So this should be randomly assigned. The colors are randomly assigned to each wire label. And essentially what we do is we encrypt the color and the wire label and concatenate the colors for the input labels to the ciphertext. Now, when the evaluator is decrypting, it has the colors for the input labels. So it knows, for example, that X0 is orange and Y1 is also orange. And it goes to the row where there are two orange colors appended to the prepended to the ciphertext, and it knows that it should decrypt that ciphertext. So while we've kind of described this technique using colors, it's essentially a random bit that needs to be sampled. So for example, the orange color can correspond to 0 and the green color can correspond to 1. And security here essentially follows from the fact that the color is independent of the wire label assignment. Okay, so now that we've understood how to garble, how does garbling work in the two-party case, let's kind of understand how to take it to the multi-party setting. So the template I'm describing here was provided by Beaver, McCauley, and Rogaway in the 90s. And it essentially provides a way to go from a non-constant round MPC protocol to a constant round MPC protocol. And the way it works is, there are essentially two phases. In the garbling phase, the parties run an MPC protocol to compute the garbled circuit as well as the wire labels for the inputs. Then once the garbled circuit and the wire labels for the inputs are computed, the parties can then just locally evaluate the garbled circuit on these input labels and compute the output. So the garbling phase is interactive, the evaluation phase is non-interactive and can be locally carried out by the parties. So the MPC ensures that, so since we compute the garbled circuit within the MPC, this ensures that the wire labels are actually private. And the reason it's constant round is because all we really need to do to garble is to sample random wire labels for all the wires. Once these have been sampled, you can essentially encrypt all the, you can compute the garble table for each gate in parallel. So this essentially gives a constant depth circuit for garbling. And now if we use any MPC protocol whose round complexity is linear in the depth of the circuit, this gives us a constant round MPC protocol because the circuit we're evaluating it on has constant depth. So one way to now get order C communication MPC for order C communication constant round MPC is the following. So we use an order C MPC for the garbling phase, which we know already exists in the honest majority setting from prior works. And this should give us an order C constant round MPC protocol. While this is true, we are essentially doing, we are making non-black box use of encryption because we have to run the encryption that is required for garbling within the MPC. So it's part of our circuit description. And this is not concretely efficient and it blows up the concrete cost. So what we would like is to move away from such non-black box constructions. And so to understand how to move away from such non-black box constructions, let's first understand how the encryption actually looks like. So if you want to encrypt a wire label on the output wire Z using input labels X and Y, we can essentially expand X and Y using PRFs and XOR it with the message to be encrypted. So Damgard and Ishai propose an MPC protocol where they basically require parties to evaluate the PRFs outside the MPC. So if the parties can evaluate the PRFs outside the MPC and input it into the protocol, they just need to XOR these evaluations, and there is no real non-black box encryption that's happening within the MPC itself. But their approach actually gives rise to the garbled circuit whose size is linear in the number of parties. So let's try and understand why this is the case. The core reason for this is that the wire labels can't be known by any single party in the clear, because that's the core requirement of the garbled circuit, right? Nobody should know, no evaluator should know all the wire labels in the clear. So what Damgard and Ishai propose is that every party essentially has its own key for the PRF. So here, each part, there are 3 parties and all of them have their own keys X1 and Y1 for the wire labels X and Y. And the actual wire labels are concatenation of the keys of all parties. Then we define the PRF expansion on the wire label as the XORs of the PRF expansions on of the labels of each individual party. So now what parties can do is compute the PRF expansions on their key of or their part of the wire label, compute the PRF and input this PRF evaluation into the MPC. And within the MPC, we just XOR all of these PRF evaluations. So the PRF evaluation is now happening outside the MPC, and that's why it's a black box construction. But because the wire labels are linear in N, the garbled circuit also ends up being linear in N. So the wire labels and then subsequently the encryptions, and because of that, the entire garbled circuit has a size that's linear in N. And this is not very good if you want to construct order C MPC. So to improve upon this, Ben Ephraim, Lindell, and Omri suggest using key homomorphic PRFs to get a garbled circuit whose size is independent of the number of parties. So here, for example, so here the scenario is that the parties have an additive share of the wire labels. So if the wire labels are X and Y, parties have an additive sharing of the wire labels. Now what parties can do is evaluate the PRFs on their share. So each party evaluates the PRF on their share. And because of the key homomorphic property, we can compute the homomorphism operation on the local PRF evaluations. And that will give us the PRF evaluation on the entire wire label. So here now the wire labels are independent of N because it's an additive sharing. There's no concatenation of individual parties labels. It's an additive sharing. So the wire labels are independent of the number of parties. But we are working in the honest majority setting where we are using some polynomial-based secret sharing scheme. And this sort of key homomorphic PRF approach does not really extend to our setting. It does not extend to the threshold setting. So while this idea actually helps give a non-black box, while it helps give a black box construction without with a garbled circuit size independent of the number of parties, it does not directly extend to the threshold setting. So what we observe is that what we really need, or what is really helpful in the threshold setting is what we call as doubly linear homomorphic PRFs. So what are they? So that has quite a few terms. So let's unpack it. So doubly linear homomorphic PRFs essentially provide a way to go from a secret sharing of the key to a secret sharing of the PRF expansion. So this is what is essentially shown here. So you have a secret sharing of the key, and each party can like evaluate, expand the PRF on the share, and that takes it to a secret sharing of the PRF evaluation on the underlying secret. So why do we call it doubly linear? This is because, again, in the threshold setting, a lot of the secret sharing schemes are polynomial based, and the relationship across different shares is some sort of linear interpolation. So we want the same linear interpolation to hold for the key as well as the PRF evaluation. So that's why it's a doubly linear homomorphic PRF. So how do we use such doubly linear homomorphic PRF? Well, let's say the parties have some threshold secret sharing of the wire labels. Now they can locally expand the input wire labels on their share to get a secret sharing of the PRF expansion, right? And this is just locally done because of the doubly linear homomorphic PRF. Now, once they have a secret sharing of this PRF evaluation, they can just add it with, or they can use these as masks to encrypt the message, and they end up with a secret sharing of the ciphertext. So the second part on why the adding this gives a secret sharing of the ciphertext is because most of these polynomial-based secret sharing schemes are also linear. So adding secret shares gives rise to secret sharing of the sum. However, while this is great in practice or on paper, we really don't know how to construct such doubly linear homomorphic PRFs. Instead, what we observe is we can actually use the LPN assumption instead of PRF. So what is the LPN assumption? Basically, if you have a key K, the LPN assumption says that the key K into some matrix A plus some error epsilon sampled from some specific distribution is essentially pseudorandom without knowing the key. So what we observe is we can now use this sort of LPN expansion to get the property that we want. And this is kind of easily visible when we kind of look at how to expand LPN using threshold secret sharing. Sorry, is there any question? Okay. We can basically see how to use how expanding LPN using threshold secret sharing kind of gives rise to a secret sharing of the sorry, I thought I heard a question. Okay. So basically, if because of the linearity property of the threshold secret sharing scheme, as long as we have a secret sharing of the key and the error, just evaluating the LPN expansion will give us a secret sharing of the pseudo-randomness. Now, this is how now parties can use LPN to compute encryptions of the output wire label. So again, let's say they have threshold secret sharing of the input wire labels and the output wire label. Now we additionally require the parties to also have threshold secret sharing of the errors. And now using the LPN by locally expanding the wire labels using the LPN assumption, specifically because of the property that we discussed earlier, they can get secret sharings of the pseudo-randomness. And now they can just use these as pads to encrypt the message. And that gives us a secret sharing of the ciphertext. So this allows us to avoid non-black box usage of encryption, and the size of the garbled circuit is also independent of the number of parties. So a prior work by Benefram and friends also uses LPN for garbling, but it uses it in the dishonest majority setting, where we can use additive sharing. So here, really what we observe is this sort of approach, how to make LPN work with like threshold secret sharing. So that kind of completes the first part of the talk, where we kind of looked into what is the structure of a garbled circuit so that it can help with instantiate an efficient multi-party garbling protocol. And what we realized is if we compute a garbled circuit where the encryption is computed using LPN, then we are able to essentially get a garbled circuit whose size is independent of the number of parties, and we make a black box usage of encryption and so on. And essentially the key idea is that we can go from secret sharing of LPN keys and errors to a secret sharing of the ciphertext. So next, let's actually look at how this garbled circuit is computed in a multi-party fashion, giving rise, which completes the entire multi-party garbling protocol. So to actually compute the garbled circuit, we divide it into 3 phases. The first phase is the pre-processing phase, where parties run an MPC protocol to compute secret sharing of the wire labels, which in our case are the LPN keys, the LPN error values, a secret sharing of the LPN error values, and finally a secret sharing of the wire label colors. So all these are basically the pre-processing data that is required to actually encrypt or compute the garbled circuit. Then using this pre-processed data in the garbling phase, parties can actually compute the garbled circuit and also the wire labels for the inputs. Finally, once these are computed, all the parties can locally evaluate the garbled circuit to compute the output. So before we get into the details of the each of the phases, I've been sort of vague about what is the exact secret sharing scheme we are using, and we need to fix that to better understand how these protocols work. So what we actually use in our protocol is something known as packed secret sharing, which was proposed by Franklin and Young in '92. So let's try and understand what that really is. So in regular secret sharing, you have a secret V, which we embed in a polynomial, and we evaluate this polynomial on n distinct points to get the shares of each party. In packed secret sharing, instead of one secret, we have multiple secrets. We embed all of these in a polynomial once again, evaluate these polynomials on distinct points, and we get the shares of all the parties. So what's really the difference between the two schemes is that here n shares corresponds in the normal Shamir secret sharing, n shares corresponds to one secret, whereas in packed secret sharing, n shares corresponds to multiple secrets, so L secrets. So let's say we want to achieve a threshold of T for Shamir secret sharing. So no subset of parties of size T or less should be able to reconstruct the secret. In this case, we essentially want these T evaluations or these T shares to be uniformly random. And we have one secret, so that gives us T plus 1 points that define the polynomial. So that is essentially a polynomial of degree T. And this is uniquely defined by any T plus 1 shares. So any a set of parties of size T plus 1 or more can basically reconstruct the secret. On the other hand, in packed secret sharing, let's say we want to achieve a threshold of T, that is, again, no subset of parties of size T or less should be able to reconstruct the secret. Once again, these T shares should be uniformly random then. Then we have L secrets to embed in the polynomial. So we have a total of T plus L points that define the polynomial. And this gives us a polynomial of degree T plus L minus 1, right? So now if honest parties want to come together and reconstruct the secret, we need at least T plus L shares to reconstruct the secret. So this is another difference between packed secret sharing and regular secret sharing, where in packed secret sharing, we have this ramp or this gap between the privacy and correctness thresholds, where if we have a privacy threshold of T, for correctness, we need at least T plus L parties. And regardless of the secret sharing we use, because we need distinct points to embed the secrets and the shares of parties, the size of the underlying field over which we're secret sharing should be at least n plus L, where if L is 1, then it corresponds to the regular secret sharing. So packed secret sharing is actually like one of the fundamental tools used to achieve order C communication in prior works. And the way this is done at a very high level is basically you have regular secret sharing. Using these, we know how to construct MPC protocols that have a communication complexity of n times C. Again, here I'm ignoring additive terms and only focusing on terms of communication that have n and C, the size of the circuit and the number of parties. So using packed secret sharing, what we essentially, the high level approach is we set the number of secrets embedded into a sharing to be proportional to the number of parties. So that means that we need C by n secrets sharings to evaluate the protocol. So we can go from an n times C communication to order C communication. But because of the gap that I mentioned previously of using packed secret sharing, the threshold is not optimal. So in with regular secret sharing, you can achieve a threshold of exactly half. Whereas with packed secret sharing, you usually have a gap. And this gap is a function of how many secrets you embed into a sharing, or L. It's a function of L. So having fixed the type of secret sharing we are going to use, let's go over actually how to compute the garbled circuit. So in the pre-processing phase, we'll need to compute the wire labels, the LPN errors, and the wire label colors. So first, let's start with how to compute the shares of the wire labels. So the wire labels are essentially LPN keys. And what we kind of observe is that we have to use a larger field because of the packed secret sharing. And in that setting, it then makes sense to use LPN over larger fields because it gives rise to better parameters. So since we are using then LPN over larger fields, the key is essentially a uniformly random vector from this field. So the problem then boils down to generating shares of random elements in F, or generating packed sharings of in F. So this is how the protocol proceeds, and this is a classical result by Hurt and Nielsen in 2006. So we in the MPC protocol, parties first locally sample a random vector. They then secret share these vectors by sending the shares to all of the parties. So that gives rise to n secret sharings. Now, if a party is corrupted, it's the adversary learns the underlying secret that it shared. So what we really need now is a way to go from these n secret sharings, where at most t of them is known to the adversary, to a way to uniformly random secret sharings. And what Hurt and Nielsen propose is to use a super invertible matrix over the field. And this essentially works as a linear randomness extractor, where we can extract out the n minus t good randomness out of the sharings and output n minus t uniformly random packed sharings. And in practice, the super invertible matrix really is like a Van der Waals matrix. So the communication complexity of this protocol is actually n squared, because every party sends a share to every other party. But because each sharing has L secrets and L is proportional to n, or linear in n, and we are able to extract n minus t outputs, which is also linear in n, the amortized communication complexity for generating one random element from the field is constant. So there's only a constant overhead to generate a sharing of a single random element from the field. So now we know how to generate the LPN keys. Now let's look at computing shares of random bits. So why do we even need to compute shares of random bits? Well, the first thing is we need it for coloring the wire labels. Essentially, those are random bits. And second, we'll be using this protocol as a sub-protocol for generating the LPN errors. But why is this problem even hard? So the thing is, we are trying to generate sharings of a uniformly random bit, that is 0 or 1, over non-binary field. That's what we mean by a larger field. It's a non-binary field, and we want a sharing of 0 or 1. So let's try to extend the previous approach. Let's say we use a super invertible matrix over F, and let's say the input sharings are packed sharings of 0 or 1. So I've only denoted them by a single bit here, just for simplicity, but they'll essentially be packed sharings. So what we observe is this approach does not really work. And the reason is, consider any row of the super invertible matrix. Now, these elements will belong over the field. And when you take the inner product with the secret sharing of the bits, you get a sharing of a field element. And there is no guarantee that this field element is really uniformly random bit. So now using arbitrary super invertible matrices over the field will not work. But we still want a way to generate shares of uniformly random bits with the same efficiency as we did for random shares. That is, for the amortized cost of generating a single random bit sharing should be constant. So how do we do this? So what we observe is actually the generator matrix of any binary linear error correcting code is super invertible over a field of characteristic 2. And so we now have we have a binary super invertible matrix essentially. And we also give a way to construct such binary super invertible matrices of size n times order of n. So that means that since the number of outputs is proportional to the number of parties, we can extract linear number of, so every iteration of the protocol outputs linear number of bit sharings and the number of parties. So since we need a field of characteristic 2, the MPC itself is now done over Galois fields of some higher order, say 2 power k, where this k actually depends on the number of parties we have, the number of secrets we're embedding, and so on. Okay, so now given this binary superinvertible matrix, how do we actually carry out the computation? So the protocol proceeds by each party sharing a uniformly random bit vector, a packed sharing of a uniformly random bit vector. We then apply the binary superinvertible matrix, and this gives us uniformly random bit sharings, and the number of such bit sharings are linear in the number of parties. So even if the adversary knows a few input bit sharings, at most t input bit sharings, we get uniformly random output as the uniformly random bit sharings as the output. So similar to the previous case, the total communication is actually n squared. But because we have L secrets and we are able to get the linear number of outputs, linear outputs in the number of parties, the amortized communication is actually constant. So now let's move on to the last piece of pre-processing data that we need to generate. That is a secret sharing of the LPN error. And now the LPN error itself is actually a Bernoulli distribution over the finite field. What do we mean by that? That means that the error should be uniformly random from the field with probability 1 over 2 power p, and it should be 0 with probability 1 minus 1 over 2 power p. So it should be 0 with high probability and or 0 with some probability and a uniformly random element with probability 2 power p. And here p is a constant. So since so now this is a protocol for actually generating a secret sharing of the LPN error. What we do is parties first run the MPC for generating packed sharing of random bits, which we just discussed previously. So they generate p such bit packed sharings. Then all these packed sharings are multiplied to get a packed sharing of a bit beta. And what I claim now is that this bit beta is biased towards is basically a biased bit where the probability that it is 1 is 1 over 2 power p. And it's easy to see why. Basically, since the input bits b1 to bp are uniformly random, for beta to be 1, for beta to be 1, all of them should be 1, and that happens with probability 1 over 2 power p. Now, since beta is biased, is a biased bit, we can now actually generate the LPN error quite easily by multiplying beta with a uniformly random packed sharing. And that gives us the LPN error. And it's easy to see why this is distributed according to the Bernoulli distribution. Because beta is biased and R is uniformly random over the field, we essentially get that epsilon is uniformly random from the field with probability to 1 over 2 power p and 0 with otherwise. So we've already discussed how to generate sharing of random bits and of random values with constant overhead. And from existing techniques, we can also carry out multiplications with the same efficiency when we're using packed sharings. And so the overall protocol has constant communication complexity. An important point here is that this is because also that p is a constant, and so it doesn't really factor into the communication complexity. So now we've discussed how to generate secret sharings of the wire labels, the LPN errors, and of the wire label colors. And now, having generated all this pre-processing information, let's discuss how to do the garbling. Well, this is pretty straightforward given our discussion before. Parties already have secret sharing of the or packed sharings of the input wire labels, as well as the LPN errors. And as we discussed before, they can now expand it in the garbling phase locally and compute a secret sharing of the ciphertext. Finally, these these shares of the ciphertext itself can be shuffled using a simple circuit, which requires like a few multiplication gates, and basically that completes garbling. But it's not as easy as that. There is one small caveat, and that is that the alignment of secrets and pack sharing is somewhat important, and it needs to be taken care of. Now, let me expand on what I mean by that. So what I mean by alignment is that, let's say we have two pack sharings, x1, x2, x3 is one pack sharing, and the secrets in the other pack sharing are y1, y2, and y3. Now, if the operation we wanted to carry out, for example, for encryption, was basically add x1 and y1, x2 and y2, and x3 and y3, since we are adding the corresponding secrets, that's straightforward. We can just add, parties can just add their share, and that would actually result in a sharing of the output. The same holds for multiplication gates, where existing MPC multiplication protocols can give efficient realizations over pack sharings. The issue, however, is when we want to compute something of this form, where we have the second secret from the first sharing and the third secret from the second sharing. So now these aren't aligned anymore, and it's not straightforward on how to actually compute these directly from the shares. And in fact, this requires some sort of interaction, and we will require that the secrets underlying the pack sharing are realigned so that this computation can actually be carried out. In fact, this is the main challenge behind using pack sharings, and a lot of the existing order C MPC protocols, even in the non-constant round setting, essentially a lot of their main challenges are in how to solve this problem efficiently. It turns out the bottleneck in this protocol is actually the number of distinct realignments we need to do. That is essentially the number of permutations we need to do over each secret. So the number of different types of permutations we need to do. And prior works have taken different approaches to solving this. Some series of works essentially bound the number of distinct realignments. Another class of works restrict the circuit type. Finally, a recent work of Goel, Polikaroniadou, and Song shows how to perform such realignments very efficiently. So there is no bound on the type of realignment. We can perform any realignment quite efficiently. And by efficiently here, I mean with the sort of constant overhead efficiency per secret in the sharing that we've been discussing so far. So this is what we actually use in our protocol. So before encrypting this wire labels on the output wires, we first realign things so that we can actually carry out the encryption. And for that realignment, we use their protocol. So this completes the garbling phase. So now that with the pre-processed information and these realignment protocols, parties can essentially now compute the garbled circuit and the wire labels for the inputs. The wire labels for the inputs can be computed using straightforward MPC by just evaluating a small circuit to select which input to reconstruct. And finally, given these, in the evaluation phase, parties can just locally evaluate the garbled circuit on the labels to compute the output. So that somewhat finishes that concludes the description of the multi-party garbling protocol. So next, let's move into the efficiency analysis and see some concrete and see how this protocol performs in practice. So we estimated the costs of our protocol, and what we found is that, and we compared it to prior works. So the two works that we compared to are in the dishonest majority setting. And as I discussed before, when the number of parties increase, the cost of these protocols increases too. So what we observe is our protocol actually achieves order C communication in the sense that it's clearly visible from our estimates that as the number of parties increase, the per party communication cost actually decreases. So the numbers here are shown for AS128, and what we see is that when there are around 200 parties, the communication in the pre-processing phase is around 750 MB per party, and it drops down to around 250 MB per party when there are around 650 parties. Similarly, in the garbling phase, the per party communication is around 80 MB for around 200 to 250 parties, and it drops down to around 40 MB when there are around 600 to 650 parties. And these are good numbers. The per-party communication is actually fairly small, which basically shows that the protocol is actually can be concretely efficient. So let's kind of understand these numbers better by kind of seeing what's the per phase split up of these costs. So here I'm discussing the numbers for the semi-honest protocol for evaluating AES 128 for 250 parties. And we assume every party has 8 threads to do the computation. So the pre-processing phase takes a total of around 1.9 minutes and has a total communication of 240 MB per party. The main bottleneck for the pre-processing phase is actually the error generation protocol, which takes 1.7 minutes out of the total of 1.9 minutes for pre-processing. And it involves a communication of around 196 MB out of the total 1240 MB communication that each party does. So why is error generation a bottleneck? This is because of the low rate of binary error correcting codes. So although we get the number of outputs that we get in the random bit generation protocol is linear in the number of parties, the concrete value is lower because of the low rate of binary error correcting codes. And we have to run the protocol multiple times to generate enough sharings of random bits. In the garbling phase, what we observe is that, or our estimates show that the computation takes a total of 1.6 minutes, and every party communicates around 43 MB of data. Here, the bottleneck, especially from a communication point of view, is realigning the secrets, which takes 28 MB out of the total of 43 MB, but it's not as significant as in the error generation protocol. Some directions for some future directions for this work are basically improving the concrete efficiency by coming up with a more efficient protocol for error generation. And it's also interesting to see if we can incorporate existing GC optimization, garbled circuit optimizations like free XOR and half gates into our protocol. Also, it'll be interesting to see if we can construct Odyssey communication multi-party garbling from weaker assumptions than LPN over larger fields. And this might give rise to more efficient protocols and is also of theoretical interest. Thank you. That ends my talk, and I'm open to taking any questions.
How do your performance estimates compare with the WRK protocol?
Oh, sorry.
Or did they not run it for that many parties?
Yeah, so they don't run with that many parties. So we actually interpolate our numbers to compare with theirs. So we interpolate around 200 to 250 parties. So what we observe is actually our protocol starts performing better around the 250 party margin. So beyond it's after that the asymptotics really start to kick in and our protocol performs much better.
Got it. Thanks.
But it's important to note that their protocol is in the dishonest majority setting, while ours is in the honest majority setting. So it's not a one-to-one comparison, but it highlights that like Odyssey communication can really help with when the number of parties are very large.
And then the BCOO-SS paper is using also the LPN trick, but dishonest majority. Is that the?
Yes.
Okay.
Yeah. But they still do have a communication complexity of n squared times the circuit size. So it's n squared times C.
And is that for them mostly pushed to the preprocessing phase? Because it looks like at least with these numbers in the garbling phase, they're not seeing that.
That's right.
Yeah. Okay.
That's right. So yeah, the n squared complexities in the preprocessing, and in garbling, I think they achieve linear.
Got it. Thanks.
Okay, are there any other questions for Aditya? All right. Well, thank you very much. I'll go ahead and stop the recording.